To begin here in example 7, which is number 26 in the book, I kind of start out by just writing up some information for us that we can look at. So just going through, it's a sentence by sentence and writing down some things. It's talking about mechanics are boring a 6-inch deep cylinder. So I put the height as being 6 inches. And then because no matter what, the height is not changing, because the height is going to stay constant, then we know the dH dt, so any change in the height is going to be 0. Okay. Going from there, it says the machine that they're using increases the cylinder's radius 1/1000th of an inch every 3 minutes. So I said the change in the radius is going to be 0.001 inches per 3 minutes, so every 3 minutes. Or we can look at it as the change in time is going to be 3 minutes. And the last bit of information they tell us is that the volume's increasing when it's specifically, we want to find the volume's increase when the diameter is 3.8. Well, since everything's in terms of almost like radius in the sense, I just rewrote to where the radius is in 1.9. Okay, so if we go up to our volume formula, volume is pi r squared h. And then we need to start taking derivative because it wants to know the change in volume with respect to time. So it's going to be dv dt. If I pull off the constants, now the constant here is not just pi, it's also pi and h, remember, because h is going to stay the same. And then all we have to do is take the derivative of the only variable that is changing, which is our radius. So it's going to be 2r and then dr dt. Okay, got to make sure we include that dr dt because we're taking derivatives with respect to time, not with respect to another variable. And just cleaning this up a little bit, then we'll get 2 pi rh dr dt. Okay, so let's go in, and now let's put in the information that we know. So 2 in pi, the radius is 1.9, the height is 6, and then the change in the radius with respect to time is 0.001. And when we put all this into the calculator, we're going to get a decimal. Looks like of 0.0716, blah, blah, blah. But now that's the inches cubed, because volume is, length times width times height, but it's going to be inches cubed. That's still, though, in per 3 minutes, because we used a change in our radius of inches per cubic, or per 3 minutes. And the question asks us is how rapidly is the cylinder volume increasing? If we really want to look at it per 1 minute, then all I'm going to do is go up here, just divide this by 3, and then we'll get the change in the volume per minute if we want to do it like that. So 0.0716 divided by 3 will get you 0.024, if you round it just a little bit, cubic inches per minute. And there's our answer. Okay, going on to the next problem. Example 8, or number 30 in the book. In this example, we're analyzing a raindrop, and specifically we're looking at how a raindrop is a perfect sphere, it's a circle, and that we want to do is find the relationship between the volume and the surface area and show that it's actually a constant. Okay, so if we write up some key information, two formulas that we know for a sphere are the volume and the surface area. The volume is 4/3 pi r cubed, and the surface area is 4 pi r squared. And again, the question wants us to find is that we want to show that the radius is the raindrop's radius increases at a constant rate. Okay, so I'm going to take the change in the volume with respect to time, take our derivative. That'll get us 4 pi r squared, and then we need to multiply it by dr dt, because r is definitely a variable that's changing. And then pretty much right here, we're actually almost to our answer, because what this is really saying right here is that our change in our volume with respect to time, look at this right here, 4 pi r squared, that is our surface area. That's the exact same thing. So what it is our surface area times the change in the radius. Okay, so our change in our volume is just equal to our surface area times the change in the radius. Well, all we have to do is just say, come over here to the side and say, well, let's let our change in our radius just be some constant, because it's going to be changing by, let's say, the change in the radius will be by every 1 inch per 3 minutes or something. It's going to be constant every single time. So when we go back to our original formula, then we're going to show that dv dt is just our surface area times a constant. And that shows the answer to the question because it's just showing that under these circumstances, as the radius increases at a constant rate. Well, it's all increasing at a constant rate, just like that. All right, so example 32, or number 32 in the book, or example 9. So to start out this problem, then what I did is just redrew the information that was given to us from the book, and then I just kind of wrote down just in sentences form. I just converted it over to what kind of notation we would use. So we've got basically a right triangle. We've got a boat that is approaching our y-axis, okay, and it's coming along the x, so x is going to be shrinking. I used R as just represent the rope because this side right here is all a rope that's being attached up here. And they tell us that the change in the rope, looking back to the problem just real quick, the rope is being hauled in at 2 feet per second. Okay, so part A says specifically, is how fast is the boat approaching? So what is our change in our x when R is instantaneously right there at 10 feet? Okay, well, if R is equal to 10 and y is equal to 6, then we can easily find x. You can use Pythagorean's theorem, or if y'all know those special right triangles like a 3, 4, 5 triangle, you know, if we reduce this is 5 for our r, this is 3, so then x has to be 4. Or, if nothing else, we can come back in here and use Pythagorean's theorem. We'll get x squared plus 6 squared is going to equal to 10 squared. So x squared is 100 minus 36, which is 64. And we'll get x then to be 8. Okay, so yes, this is a 3, 4, 5 triangle. Okay, so now let's go to our problem. Our basic formula we're going to use is Pythagorean's theorem. So x squared plus y squared is equal to r squared. Some things that we know, obviously, is that y is going to be constant. It's not a variable. Our only variables that are changing are x and r, because y is just the height. You're not going to be able to change the height of the dock. I'm going to go ahead and solve this for x squared, because that's what our problem is asking, is how fast the boat's coming in. And now let's take our derivative. So 2x dx dt is going to equal 2r dr dt, and then I'll go and just put minus 0 because y is just a constant, so we're just going to put minus 0. Okay, finishing this out, then we have 2x dt is going to equal, if I divide both sides by 2, then you're going to get r over x dr dt. Okay, let's plug in some information. So let me bring this down just a little bit. So the change in x with respect to time is going to be r, which is 10, over x, which is 8, times the change, which is 2. If I plug that all in my calculator, then I'm going to get 2.5 then feet per second. Now I'm going to come in here, and actually we got to think about the context of the problem. As that boat is coming in, is it shrinking the distance or is it increasing the distance? Well, because we are shrinking the distance to the dock, but what I really want to do is write this as a negative 2.5 feet per second because we're closing in on the distance. Okay, so you can either do one of two things. You could look at your answer, analyze your answer, and make sure it's in the correct unit, so either positive or negative. Or what we could do is, if I wanted to go back up to the original problem, what I could have done is made our change in our rope with respect to time, made that up there negative. Okay, because obviously as you're pulling in the boat, you're shrinking the rope's length. You're not going to need 10 feet every time. It's going to be 10 feet, then 9 feet, and 8 feet because you're pulling in that rope. So either you make that negative and then use it in your equation as being negative, or you just go to your answer and then make sure you have it in the terms of the right positive or negative. Okay, so we're going to box that up. And that answers our question for how fast that boat's coming in. Basically 2.5 feet per second, and the negative says it's definitely coming in. Going into part B, what it wants us to do is analyze the change in specifically this angle that's formed up here in the right triangle when this exact situation is happening. Okay. Well, now instead, since we're looking at our main formula that we're going to use, because we're looking at an angle, we can either use sine, cosine, or tangent. I just happen to pick sine, so I just use the main formula that sine of theta is going to be opposite over hypotenuse, so x over r. And if I go in there, now start my derivative. So the derivative of sine is cosine theta. And over here I have a quotient rule. Oh, sorry. Because theta is actually changing obviously it's a variable that is not constant. We need to write it as also then d theta dt. Okay, so the derivative of sine of theta is cosine theta, and then times the derivative of your angle, which is just 1, but then d theta dt. Okay, and over on the right we have the quotient rule because both x and r are changing. The only variable that's not was y, but x and r are both changing. So I'm going to do bottom times the derivative of the top minus top times the derivative of the bottom, all over the bottom squared. So then solving this out just a little bit more, d theta dt is going to be r dx dt minus x dr dt over, and since I'm dividing both sides by cosine, then we can write that as r squared cosine theta. Well, according to everything that's in here that we need to find, we need to know r, which we already know already, r is 10. dx dt, we just found that, it's negative 2.5. X, we know it's 8. dr dt, we know r. And then let's look at cosine theta. What is cosine theta? We'll just go to our picture. Cosine theta is what? Adjacent over hypotenuse. So cosine of theta is 6 over 10. So we're going to use that also as well. Okay, so d theta dt is going to equal r, which is 10 times dx dt, negative 2.5, minus x, which is 8, times dr dt, which is 2, over r squared. So 10 squared times cosine theta, which is 6 over 10. And if we put this all together, then we're going to get d theta dt to be either, you can write it as negative 9 over 60, or we can say that d theta dt is equal to a negative 0.15, and I guess we can say radians per second. All right, that problem is finished. Let's keep going on.